For centuries, our understanding of light and its interactions with matter have been shaped by the properties of naturally occurring materials. These materials, like glass or water, possess a refractive index that dictates how light bends and slows down as it passes through them. However, the advent of metamaterials has ushered in a new era in optics, one where we are no longer limited by the constraints of nature. Metamaterials, artificially engineered materials with unique electromagnetic properties not found in nature, have revolutionized our ability to manipulate light in unprecedented ways. At the forefront of this revolution are zero-index metamaterials, a class of metamaterials that exhibit a refractive index of 0. This extraordinary property arises from their unique structure, meticulously designed at the nanoscale to interact with electromagnetic waves in unconventional ways. Unlike conventional materials, zero-index metamaterials allow light to propagate through them without any phase accumulation, effectively making the light travel instantaneously across the material. This phenomenon, known as zero-phase delay, has profound implications for various fields including telecommunications, imaging, and energy harvesting. Zero-phase delay, a hallmark characteristic of zero-index metamaterials, describes the unique ability of these materials to transmit electromagnetic waves without any phase shift. In essence, light entering a zero-index metamaterial exits the material at the same phase as it entered, as if it had traveled through a vacuum. This phenomenon arises from the precise arrangement of the metamaterial's constituent elements, which interact with the electric and magnetic components of the electromagnetic wave in a way that cancels out any phase accumulation. The implications of zero-phase delay are profound. It implies that the wavelength of light inside a zero-index metamaterial becomes infinite, effectively stretching the wave to an unbounded extent. This has significant consequences for applications like optical interconnects, where information can be transmitted without any delay or distortion. Moreover, zero-phase delay leads to an infinite phase velocity, meaning that the speed at which the phase of the wave propagates through the material is limitless. While this does not violate the fundamental speed limit of light in a vacuum, it opens up fascinating possibilities for manipulating the temporal properties of light. Snell's law, a fundamental principle in optics, governs how light bends when it passes from one medium to another with a different refractive index. It states that the ratio of the sines of the angles of incidence and refraction is equal to the ratio of the refractive indices of the two media. However, in the case of zero-index metamaterials, Snell's law takes on an intriguing twist. When light passes from a conventional material into a zero-index metamaterial, the angle of refraction becomes 0, regardless of the angle of incidence. This means that light entering the zero-index metamaterial does not bend, but instead continues to travel in a straight line, effectively eliminating refraction. This phenomenon arises from the fact that the refractive index of the zero-index metamaterial is 0, leading to a 0 value for the sine of the angle of refraction in Snell's law. Moreover, zero-index metamaterials exhibit total transmission at any angle of incidence. Unlike conventional materials, where some light is always reflected at the interface, zero-index metamaterials allow all incident light to pass through without any reflection. This property makes them ideal for applications like perfect lenses and anti-reflection coatings. Achieving a refractive index of 0 in a material might seem like an impossible feat, but metamaterials have made it a reality. The key lies in engineering the material's structure at the nanoscale to manipulate its electromagnetic properties in a controlled manner. There are several approaches to achieve 0 refractive index, each relying on different physical mechanisms. One approach involves creating a metamaterial with both 0 permittivity and 0 permeability. Permittivity describes a material's ability to store electrical energy, while permeability describes its ability to support the formation of magnetic fields. By carefully designing the metamaterial's structure, researchers can create artificial resonances that effectively cancel out the material's intrinsic permittivity and permeability, resulting in a net refractive index of 0. Another approach focuses on achieving 0 permittivity while maintaining a non-zero permeability. This can be achieved by creating metamaterials with metallic structures that exhibit plasmonic resonances. Plasmons are collective oscillations of electrons at the surface of a metal. and by tailoring the shape and size of the metallic structures, researchers can induce plasmonic resonances at specific frequencies, leading to a vanishing permittivity and a near-zero refractive index.